Once we check, Mr. Aryan Kumar, is it low? Good morning.
Now, okay. Now, okay.
Now it's okay. Okay, then. Yeah, come to here. Yesterday, I think I started semiconductor devices. Just some introduction I gave. Good. Come to here. So, semiconductors, how they ruled the total electronic field. Here, going to discuss, right? And coming to here, what are the properties of semiconductor? How to explain the conduction in the semiconductor? Coming to here. Basically, they found that in the periodic table, the fourth group elements means I think uh, carbon, am I right? Silicon, germanium, next followed by I think antimony, bismuth. What I'm saying, correct or wrong? No one is responding here.
Yes, sir.
Yeah, these fourth group elements are behaving like the semiconductors. Okay. And in the fourth group elements, what they found in chemistry, if you see the bond structure and crystalline structure, there, suppose if I take the germanium crystal, there the germanium atoms are bound with the surrounding neighborhood atoms, like by forming the covalent bonds like this. Since there are fourth group elements, we can say that according to chemistry, there are 4 valence electrons in the valence orbit. And the 4 valence electrons are forming with the neighboring germanium, same family. Okay, germanium crystals. In the germanium crystal with the germanium atoms, covalent bonds like this. These are the covalent bonds formed by one germanium atom. Again, the other germanium atoms also form the covalent bonds with the other germanium atoms like this. Okay, all. I'm not drawing total crystalline structure here. Sorry, total bonds here. I just drew here for only one germanium. Okay, germanium centered here, placed at the center. So according to chemistry, the covalent bonds are strong. Okay, compared to the other bonds. So covalent bonds are strong means here the bond structure will not be broken easily. You have to supply more amount of energy. Okay. Diamond is completely different. That there the strong structure is very strong, not like diamond. Here you can supply some less amount of energy to if you want to break or if you want to eject one electron from the bond. Okay. Right. There the structure is very strong. And that's why it is called diamond. So here in this germanium, what they said, it is actually one fourth group element considered as a semiconductor. What they said, suppose if you supply some amount of energy, in what way, sir? That is your wish, from some external source or in the form of thermal energy. Okay, the thermal energy that what you get from the room temperature, what I'm saying. Okay. So first, if you go to the low temperatures, all the electrons, okay, in the valence orbit. Why we are discussing about the valence orbit? Because those electrons only are interested to come out. Why? Because they are loosely bound to the nucleus. Okay. Not with the electrons from first orbit or second orbit. They are strongly bound to the nucleus. That's why it is not so easy to remove those electrons. Usually we give a blow to the weak persons only. In the same way here, we give the blow to the valence orbit electrons. Why? Because they are loosely bound. Very easy to take them out. That's why we are discussing about the valence orbit electrons. So at low temperature, all the electrons in the valence orbit are not interested to come out of orbit. Reason behind is the energy what you are supplying at low temperature is not sufficient to overcome the force of attraction of the nucleus. Okay, that is the reason behind. Means that one what we say, is it excitation energy or what is the other name in chemistry, Nana? Ionization
First,
energy. Ionization energy. Am I right?
Right,
The
sir.
energy required to eject an electron from valence orbit is ionization energy. Excitation energy means to excite the electrons from the higher orbits. Okay, that ionization energy you won't get at low temperatures. This is the problem. Okay, if electrons are not interested to come out from the orbit, then you can find that there are no free electrons in the crystal. If there are no free electrons, there will be no current even though you apply the potential difference between the two ends of the crystal. Yeah, that is the germanium crystal. That's why here you are not finding out no current through the crystal even though you maintain the potential difference. Okay, that's why we say here they behave as insulators. Oh, obviously G is gallium, this is Ge na. Ge is germanium, G stands for gallium. I did not write anywhere G. I wrote here all are Ge only. Ge is germanium. What, Bhargav?
Sir,
Right. That to Ga, I think gallium for the representing letter. Yes, mister.
Sir, means at low temperatures, means if we supply very high energy also, still it won't come out, sir.
No. What I'm saying, at low temperatures, here it is not getting the thermal energy. That's why they are revolving around the nucleus in the valence orbit only. That's why naturally we are not finding out any free electrons in the conductor, means in that in that crystal. That's why it won't send any current.
Okay.
Okay, naturally, what I'm saying, at low temperatures.
Okay.
Right, at the temperature here, if you maintain the potential difference, there are no free electrons to conduct the current. That's why no current will flow. Right?
Okay, sir. Understood. Yes.
A simple thing, Nana. All these we are actually using for the electronic devices. Electronic devices we fix on the motherboard. On the motherboard, where you get the energy? From the room temperature or from the excess heat what you are getting from the motherboard. Means that is obviously the thermal energy only. That's what I'm saying. You are supplying
Okay,
the
sir.
thermal energy means you are increasing the temperature. Now you understood?
Yes, sir. Understood.
All right, come to here. There are no free electrons. That's why here that implies the crystal behaves as an insulator. The same thing what he is saying, next point here, when you come to room temperatures, okay, here you have to focus more. What is that point, sir? At room temperature, what I say, you will get less amount of energy. Yes, we accept, but that is sufficient to eject the free electrons, sorry, to eject the valence electrons particularly. The energy, the thermal energy, what I say, the thermal energy absorbed by the crystal releases the valence electrons and form free electrons. Of course, they in result means valence electrons, and in turn the free electrons are available to conduct the current. That's why here, when you maintain some potential difference to send those free electrons in one particular direction, then immediately you will get some current, means it behaves as, that implies the same crystal now behaves as a conductor. Okay, this is what he's saying. But if you think wisely here, from where those free electrons are coming out, if you see in the crystalline structure, they are coming out of valence band. Okay, that's why here that valence band requires some energy to eject an electron, this germanium suppose atom. Okay, not to break the covalent bond, just to eject an electron from the valence orbit. Okay, once the electron comes out of the valence orbit, then here this electron is coming out of the covalent bond, leaving some empty space here. Okay, once again I am repeating, when some amount of energy, thermal energy, is absorbed by the crystal, and that is sufficient, which is equals to, simply I am saying in chemistry word, saying the chemistry word, that is the ionization energy. By that, the valence electron will come out. Valence electron is coming out means that does not mean the covalent bond is broken. Okay, just electron will come out. Once the electron comes out, that is not called as valence electron, that is called as free electron. So here the free electron will be available for us, and here still the covalent bond exists there, so that this electron, the other electron of other germanium atom, still maintain the covalent bond with the empty space there without breaking the bond. Why? Because that bond is strong, covalent bond is strong. Okay, so here all this story is related to energy concept. How much energy is required to break the covalent bond? How much energy is required to eject an electron from the covalent bond? Means from the valence orbit. Okay, so the total story is related to the energy. That's why he's trying to explain with the energy levels by taking a graph like this. This is a graph where just he is taking the energy levels only without taking anything on the x-axis. Nothing is there on the x-axis. And on the y-axis, he is taking the energy in electron volts. Okay. and he is trying to draw the energy levels of the electron volts with some, suppose that is 13.6. Suppose he tried to draw one line like this. 13.61, he tries to draw one more line like this. 13.59, he tries to draw one more line like this. 13.58, 13.65, like many lines he tried to draw parallel to x-axis. That line represents energy of one electron. Likewise, in the crystal, there are many valence electrons are there. For all valence electrons, here he calculated the energy, and all energies is not getting exactly one particular value because of that room temperature. All are about to excite from their original state, means from their valence orbit, and they are trying to ionize the atom, okay, by acquiring the ionization energy. That's why R in excitation. Excitation means the energy according to uncertainty principle is not particularly like 13.6. That's why you will get around 13.6 plus or minus something. Okay. So with all those energies pack, if you draw here the combination of all lines, you can find like one bunch of energy levels. That bunch of energy levels of valence electrons in the crystal called as valence band. Okay. So here VB is nothing but valence band, which is nothing but it is the pack of bundle of, better I say, of energy levels of all valence electrons in the crystal. So understood this point, Nana? What is meant by valence band? Or do you have any doubt regarding this point?
సార్
Understood.
అది
Yes, yes.
సార్ బ్యాలెన్స్ బ్యాండ్ అంటే అది ఆ పర్టికులర్ రేంజ్ లోనే ఎలక్ట్రాన్స్ ఇస్తాయనా?
అంటే అది రేంజ్ అని కాదు, ఇట్ ఈస్ జస్ట్ నథింగ్ బట్ ఎనర్జీ స్టేట్ కదా. నువ్వు ఆర్బిట్ అని దేని అంటున్నావు? సమ్ ఎనర్జీ స్టేటే కాదు.
ఎస్ సార్.
దాట్ ఎనర్జీ స్టేట్ ని నేను గ్రాఫ్ లో డ్రా చేసుకున్నాను అంతే. దాట్స్ ఇట్, నాట్ లైక్ అన్ ఆర్బిట్.
ఓకే.
సో అన్సర్టెనిటీ ప్రిన్సిపల్ వల్ల ఏమవుతుందంటే ఆ ఎలక్ట్రాన్ ఇట్ కాంట్ గో అవుట్. సపోజ్ సింపుల్ లాజిక్ నాన్న, దీని ఎనర్జీ 13.6 ఎలక్ట్రాన్ వోల్ట్స్ అనుకో ఫర్ ఎగ్జాంపుల్. ఓకే, దీనికి -13, దీనికి ఫర్ ఎగ్జాంపుల్ 0.4 ఎలక్ట్రాన్ వోల్ట్స్ ఇఫ్ యూ యాడ్, ఇట్ విల్ కమ్ అవుట్ ఆఫ్ ద ఆర్బిట్, బికమ్స్ ఫ్రీ ఎలక్ట్రాన్. ఓకే, 0.4 కాకుండా డ్యూ టు దిస్ రూమ్ టెంపరేచర్ దానికి ఆ ఇన్స్టెంట్ లో 0.2 ఎలక్ట్రాన్ వోల్ట్స్ వచ్చింది. ఏమైంది? ఇట్ కాంట్ గో అవుట్ అండ్ ఇట్ కాంట్ స్టే ఇన్ దట్ ఆర్బిట్. అంటే కంప్లీట్ అన్సర్టెనిటీలోకి వెళ్ళిపోతుంది కదా.
ఎస్ సార్.
క్వాంటమ్ థియరీ ప్రకారం 13.6 తర్వాత ఇక ఆర్బిట్ ఉండదు. ఓకే, సో హియర్ ఇది ఏరే ఆర్బిట్ లోకి వెళ్ళలేదు, లోయర్ ఆర్బిట్ లోకి వెళ్ళలేదు. బై లూజింగ్ ద ఎనర్జీ ఇట్ షుడ్ బి స్టే దేర్ ఓన్లీ అంటిల్ ఇట్ గెట్స్ 0.4 ఎలక్ట్రాన్ వోల్ట్స్. అంటే దానికి 13.6 ప్లస్ 0.4 అంటే -13.2 అయినా కూడా ఇట్ హ్యాస్ టు స్టే దేర్. సారీ, 13.3 అయినా కూడా ఇట్ హ్యాస్ టు స్టే దేర్ అంటిల్ ద ఎనర్జీ టర్న్స్ టు -13.2. ఇది అర్థమైందా ఈ కాన్సెప్ట్?
ఎస్ సార్.
అంటే ఇప్పుడు దానికి ఎగ్జాక్ట్లీ -13.6 ఎలక్ట్రాన్ వోల్ట్స్ అని నువ్వు చెప్పగలుగుతావా? దట్స్ వాట్ ఐఎమ్ సేయింగ్. By absorbing the energy from the room temperature, means thermal energy. Will you say exactly it is 13.6? What,
No,
you are
sir.
not responding. Yes. అందుకే the energy of that particular valence orbit, దానికి he is taking a pack of energy levels. అంటే plus or minus something. What wrong?
ఎస్ సార్.
ఏం మాట్లాడటం? రైట్, గుడ్. ఇది దీని యొక్క స్టోరీ. అంటే again if you come to the orbit explanation, you can say that this is actually energy pack of whom? Which electrons? Valence or some other
Valence.
electrons?
బ్యాలెన్స్.
Valence.
Kabatti, if you want to explain with the orbit story, you can say all the valence electrons exist in this valence band. Simple. Okay. So
Okay,
those
sir.
are all valence electrons. Right. ఇప్పుడు valence నుండి, for example, if you want to ionize, means turn it to a free electron, you have to supply some amount of energy or not?
ఎస్ సార్.
In my previous example, I said
Yes.
that it is 0.4 plus 0.4 electron volts I have to supply. Until the energy level becomes minus 13.2 electron volts, in between there is no orbit. Am I right?
ఎస్ సార్.
That gap value is 0.4. Correct enough? Whatever the additional energy required to make it free.
ఎస్ సార్.
That energy means if it is the energy of valence orbit, until you take plus 0.4, you won't find any orbit. Until here you can find some gap. That gap he is naming it as forbidden energy gap. Okay. This is FEG. What is that FEG, sir? Forbidden energy gap. So FEG, I am writing here. Forbidden. Okay, not Joe Biden, Nana. Forbidden energy gap. Okay, what is this, sir? I already explained here. Means once suppose electron turns into free electron, it won't stay in this forbidden energy gap. It will become free. It will become free means again calculate the energy of all free electrons, available free electrons in the crystal. Okay. Again, free electrons won't possess the same energy. Why? Because required energy is 0.4. Sometimes it may get 0.5, sometimes it may get 0.6, sometimes it may get 0.7. Means 0.5 is utilized for ionization. Leftover energy for the electron extra is 0.1 in this case, 0.2 in this case, 0.3 in this case. Extra you are getting here. Again, all the free electrons are not having the same energy. Are not having the same energy means again I have to take the pack of bundle of energy levels of free electrons. That bundle here I am drawing of free electrons in the graph. Okay, here that bundle of energies of all free electrons I draw here. This is the bundle what I am taking. Okay, that bundle is called as the conduction band. CB is what, sir? You wrote there. CB is the conduction band. And here I forgot one point to write there. In this forbidden energy gap, no free electron is available. Better I erase and write. No free electron is available in the gap. Will you find any electron in the gap, Nana?
No, sir.
Surely. All day, if you give the energy, means that if you want to make it free, you have to supply the energy more than forbidden energy gap. Am I right?
Yes, sir.
So there, once you give, those electrons will come to the conduction band, means that energy level, I am calling it as conduction band. That is the energy pack of, it is the bundle of energy of free electrons. That's why if you want to say where the free electrons exist, I can say that since it is the energy of free electrons, I can say once they are ionized, the atom is ionized, all the free electrons will reach to the conduction band here like this. This is the conduction band. This is a fundamental story with the energy, Nana. Okay. Do you have any doubt in the fundamental concept in semiconductors?
No, sir.
Sir,
If you have, you can raise. Yes.
No, sir.
Yes.
sir, once can you
Sorry,
tell
what?
FEG, sir? Yes, sir, FEG, forbidden
Forbidden
energy gap.
energy. Forbidden
Sir.
energy
Means
gap is the minimum amount of energy required to take out an electron from the valence band. Means from the
okay.
valence
Means
orbital.
in your example, means it in your example 0.4, no, sir? This gap.
Yes. That forbidden energy gap is 0.4 in my example.
Okay, sir. Okay, sir.
So if you give 0.3 electron volts, no electron will come out now.
It won't come out.
That's why here in this forbidden energy gap, no electrons will be available.
Okay,
That's
sir.
what I wrote.
Understood. Okay, sir.
Good. Then again, coming to here, that energy band story, this band theory, according to the band theory, once one theory is developed, that should explain all the concepts, Nana. Means that should be valid for all types of materials. Means even for conductors, semiconductors, and insulators. You should not give the theory for one particular element. Means one type of conductors. That's why here immediately they asked, if you give this kind of theory, band theory with valence band and conduction band, immediately they asked, with this band theory, will you explain the conductors, the conduction of electricity in the conductors? Then immediately they try to explain like this. Yes, master. There in case of conductors, what we are saying, suppose if you draw the band theory graph, what they said, this is our valence. I did not say any word like hole until now. Why you are asking about holes, Mr. Bhargav? Where I said about the word hole? Where I told any word like hole in this concept not till now? నేనేమైనా ఎక్స్ప్లెయిన్ చేశానా మీకు?
No,
No,
sir.
అసలు ఇంతవరకు హోల్ అనే వర్డే రాలేదు కదా నా మౌత్ నుండి. So wait, Mr. Bhargav. Right. Come to here. This is actually the valence band. And here they told this is the blue color is the conduction band. This conduction band and valence band, they merge with each other like this without forbidden energy gap, what they told. This is the blue color is conduction band. Okay. This is what they explained. Of course, this is the energy, Nana. They took on y-axis in electron volts. Okay. The merge means in this case, the forbidden energy gap is equals to 0 in conductors, what they explain. means from the valence orbit very easily you can take out the electron. Very small amount of energy, even at low temperatures you can supply that much amount of energy. That's why in conductors, even at low temperatures also, you can find many free electrons. Okay, lot of free electrons will be available. That's why the conduction is based on the concept of only the electrons. And that too in conductors, all they are not fourth group elements. That's why there are no covalent bonds in conductors. That's why here, once the electron comes out here, there will be still, you can't say like there will be still the covalent bond between the atoms. Okay, did you follow my concept, Nana?
Yes, it
They are
followed,
not,
sir.
yeah, they are not fourth group elements. That's why in conductors, there will be no covalent bonds. No covalent bonds means no existence of covalent bond. That's why once electron comes out, That's it. No need to discuss about the covalent bond, existence of covalent bond. That's why here the covalent bond, and once the electron comes out of covalent bond, what happens? Like Bhargav, no need to ask in conductors. Okay. So they easily explained with a simple word FEG is equals to 0 in conductors. Okay, accepted. No flaw here in this explanation. That's why this band theory, using the band theory also, you can explain the conductivity in the conductors. Accepted. Okay, pass marks it got. Okay, so will you explain in insulators? Why not? Sure. Why the insulators are not able to send the current unless you raise the temperature to high temperatures? At low temperatures and normal temperatures, why they are not conducting the current? If you ask, they explain yes, why not? Sure, using the band theory. Again, they try to explain like this. Master, this is the covalent band, master. And this is the valence band, and these are the colors, what we took for the two. Okay. And here they found this is the forbidden energy gap. It is not equal to 0. And that forbidden energy gap, they found it is greater than 5 electron volts in insulators. That much energy you can supply only at high temperatures, not at ordinary temperatures, normal temperatures, and low temperatures. Not possible. That's why here the valence electron will not come out from valence orbit. That's why in that case you say here this is complete full of valence electrons, and free electrons in the conduction band you say 0. There are no free electrons, no conduction of current. That's why insulators are not possible to send the current through the material. Okay, this is the thing in insulators. So in this case, I say the conduction band is completely empty. Again, I got small doubt. Here the spelling is correct, Nana?
Correct, sir.
Conduction band is completely empty. Okay. And valence band is full of electrons. Okay. Whereas here there is no difference between valence band and conduction band. Almost they merge with each other. That's why there is no discussion here, such type. Okay. If you want to write, you can write both valence and conduction bands are filled with electrons. Okay. Only at high temperatures, because of the required thermal energy, acquiring the required thermal energy at high temperatures, the insulator behaves as a conductor. This is what they said in case of insulator. Practically, that is correct only. At high temperatures, increase the temperature of insulator. Yes, free electrons will be available in the insulator and they send the current. And even here also, they are not fourth group elements. That's why there is no covalent band story. So the covalent band story will come only in the semiconductors. So in case of semiconductors, what you say, sir? Yes, come to here. This is conductors, this is insulators, and come to the semiconductors here. In case of semiconductors, the forbidden energy gap is neither zero nor much high.
1 electron
Okay,
volt,
they
sir.
found it. Super, Mr. Bhargav. In case of semiconductors, FEG, not exactly 1 electron volt, is nearly, approximately, I write, approximately equal to 1 electron volt. Means like 1.1, 0.9, 0.8, like around 1 electron volt, you will get semiconductors. This small amount of energy you can find even at room temperatures also. Okay, that's why there the free electrons are available. Okay, at room temperature. And more important here, not only FEG is less, but also the valence electrons, okay, come out of atom from covalent bonds. Covalent bonds without breaking the bond. So there again, I'm going back to my theory. I already told that electron comes out, the bond still exists. Okay. So one electron is not pairing with another electron in the covalent bond, pairing with the empty space. Okay. So that empty space, because of vacation, who vacated that place? Valence electron. Because of vacating the space in the valence band by who? The valence electron. Means all the story is roaming around valence. Okay. In the valence band by the valence electron. Now I am calling it as is called. Now you are getting the word, Mr. Bhargav, your famous word. That's why I'm changing it to the pink color. Is called the hole.
Yes, sir.
Yes. ఇప్పుడు అడగచ్చు if you want, who is this hole? Okay. But problem is, once some empty space is formed after emitting one electron from the valence band, okay, forming one empty space there. Here, suppose one electron comes out, empty space is formed. Okay, that empty space is still paired with the electron and still maintaining the covalent bond without breaking. But compared to the other covalent bonds, it is weak. Why? Because there, if you see, there are 2 electrons in each covalent bond. If there are 2 electrons, then the bond will be very strong. But here in this covalent bond, why? Because 1 electron is taken out. That's why this bond is weak. So this weak bond where the valence electrons exist, okay, that hole always tries to capture another electron from the valence band, not from the free electron. The free once come out or step out, there is no stepping. Okay, means it is already stepped out now. It came to the conduction band. That's why here the empty space, suppose here 1 electron came out, we are calling that empty space as hole. That hole actually in the valence band, formed in the valence band, better I write one more point here, the holes are formed in the valence band only. Why? Because you are very smart. You may ask one more question. Sir, by de-excitation here, suppose from the conduction band, the electron again jumps to the valence band. Then hole will be formed in the conduction band. What do you say, Ra?
No, sir.
Why? Why the hole is not formed in the conduction band?
Means, sir, whole means it is only specific to valence band, sir. Means whole from definition only you
Not,
told, sir. Even it
yeah,
vacates.
not only valence. Yes. That hole will be formed because of what?
Vacating of
By
electron
the vacation of a vacated electron. Where?
in the valence band, sir.
When the valence band means that is where?
Covalent bond.
In the covalent bond.
Covalent bond.
Yes. Okay. Since covalent bond is not broken, still empty space is valid there. Am I right? Whereas free electrons are not in the covalent bond. Na?
Yes, sir.
That's why once the free electron again jumps back, here the holes are not formed. Now you understood? Will you ask that question?
No, sir.
So here, why the hole is formed in the valence band? Because of the covalent bonds. Bond is not broken. That's why still the hole is sustained. Okay, if the bond is broken, because there is no question of hole. Am I right?
Right.
Yeah, by the emission of electron, suppose the bond is broken, it has a story ledu, hole ledu, na bond ledu. Bond is broken, and then you can get two free electrons here. There is no question of hole. Problem anta ekkadocchindi? Even though the electron comes out of the covalent bond, the bond is sustained. Sustained annappudu this electron is pairing with whom? We have to explain. Pairing with the empty space. Yavada empty space? I am calling it as hole. Okay. ఇప్పుడు వాడంటాడు హియర్, ఇది మరి చాలా స్మార్ట్ గా ఉంటుంది. అబ్జర్వ్ దిస్ పాయింట్. హోల్ ఈజ్ వాట్? జస్ట్ ఎంటీ స్పేస్. ఓకే, కానీ దట్ ఎంటీ స్పేస్, వాట్ ఐ సెడ్ హియర్, కంపేర్డ్ టు అదర్ కోవలెంట్ బాండ్స్, దట్ ఈజ్ వీక్. That's why it tries to capture the other valence electrons to fill its empty space and to become strong. తను వీక్ గా ఉన్నాడు కాబట్టి వేరే వారి దగ్గర నుంచి తీసేసుకోవడానికి ట్రై చేస్తుంది. ఇట్ ఈస్ ఎ కామన్ హ్యూమన్ నేచర్ అండ్ దట్ ఈస్ ద నేచర్ ప్రాపర్టీ. ఓకే, సో హియర్ అకార్డింగ్ టు ద natural phenomenon here, it tries to capture one electron from this covalent bond or from that covalent bond or then this covalent bond or the other covalent bonds. From anywhere it tries to capture. By that what happens? Here one electron jumps to this covalent bond. Now it becomes strong, but observe here what happened. Electron is vacated from that place. Means what happened here? Hole is formed or not? Indirect ga, smart ga think chey. Electron is moving in this direction. Hole is moving in this direction. Will you accept my explanation?
Right, sir.
What is the charge on electron? Negative or positive?
Negative, sir.
Who will try to move in opposite direction to the negative charge?
Positive charge.
So what is the wrong if I say the charge on the hole is positive? Will you deny my point?
No, sir.
That's why even though it is empty space, consider the hole as a positive charge. That's why if I ask what is the charge on electron, okay, don't say the value, it is simply negative charge. What is the charge on hole? Don't say the value, it is simply positive. How much if I ask? Directly you can say 1 plus 1.6 into 10 to the power of minus 19. Why you are saying that value, Ra? It is vacated by the electron. That's why here lack of 1.6 into 10 power of minus 19. That's why I am saying the charge on hole is 1.6 into 10 to the power of minus 19. Will you accept that point?
Right, sir.
Its value is plus 1.6 into 10 to the power of minus 19 coulombs. This is the charge on hole. So compared to the conductors you observe there, simultaneously the free electrons are available and they are moving, and the hole is also moving from one bond to the other band in the valence band. Means you are finding out the moment of hole and the moment of electrons if you maintain some potential difference. By that, what happened? Practically available, suppose 3 electrons in the crystal. I say those 3 electrons came to the conduction band from valence band. So 3 places are vacated here. Through holes are formed there in valence band. Well, a hole is considered as positive charge here and electron is negative charge. When you maintain the potential difference, both will move. Both will move means indirectly I am getting the movement of 6 charged carriers instead of 3. What do you say?
Right, sir.
Yes, practically available 3 electrons. But when you maintain potential difference, 6 charge carriers are moving. Means compared to conductors, there only free electrons move. Here free electrons and holes move. That's why here conduction increases. How, sir? If you increase the temperature, more electrons will come to the conduction band. More holes are formed. More electrons, more holes. Number of charge carriers for carrying the current is increased. Means conduction is increased in semiconductors. Is it okay, Nana?
Okay, sir.
That's why here with the increase of temperature, he said the conduction is increased compared to the conductors. This is what they said based on the band theory and covalent bonds and the formation of holes. Okay. Related to this concept, what type of questions they ask in exams are tomorrow we will discuss. Means not tomorrow, in the next class. Okay. Right, if you want to take the pages, you can take. Just today we have theory more, that's why we got only 2 pages here, theoretical pages. This is the first page and it is the second page. That's it. So shall I stop the class, Nana?
First page.
Okay.
First page, yeah. Okay, this is the first page. And once again, this is the second page.
Okay.
So okay, bye Nana, bye everyone.
Bye, sir.
Bye, sir.
Bye.